This conference will now be recorded.
Very good evening, students. We had been discussing ray optics for a long time. So today we'll complete this ray optics part, discussing reflecting telescopes. So we have already learned regarding this telescope what we have already learned. We have learned what is a telescope. So telescope is an optical device which enables us to see distant object clearly. Actually what it does, it actually increases the angular magnification of a distant object, and that's how we could see very clearly. Okay, so now we had already discussed the types of telescope we have. So there are two types mainly, refracting type and reflecting type. As I had already discussed, refracting means refraction of light is being used. So in this case lens was used. Okay, lens is used in this refracting type telescopes, and in reflecting type telescope obviously mirage will be used, as the reflecting property of the light is being used in this reflecting type of telescopes. So in the refracting telescopes we have seen there are two types of refracting telescopes. One is astronomical telescope and terrestrial telescope. Telescope. So for the timing we have discussed astronomical telescope because this is not there in the syllabus. So we have already discussed it. Astronomical telescopes are those telescopes which are used to see heavenly objects or astronomical objects. Basically in the scientific research is to see the planets, stars and other cosmical objects. And see, when we have discussed this telescope, astronomical telescope, we have seen one thing, that objective lens has to be or has to have very large aperture, okay, for better magnification that we have seen. But when we go for very large apertures of lens or very big lens, then there are certain things which limits the utility of this refracting type of telescopes. Okay, so there are certain demerits in this refracting type of telescopes. We'll discuss first those things. Before that, let me tell you, to overcome those demerits present in the refracting telescopes, reflecting type telescopes are being manufactured or are being discovered, and first reflecting type telescope was made by Sir Isaac Newton in 1668. Okay, so the first reflecting type telescope was made by Sir Isaac Newton. So there are two reflecting types of telescopes. One is Newtonian telescope. Another one is Cassegrain telescope. So these are the two telescopes which are made or manufactured or discovered later to overcome various demerits present in the refracting type telescopes, where we have used a large objective lens. Okay, so let us see what are the demerits. First demerit is spherical aberration. So what is spherical aberration? Look, what is spherical aberration? When I have a large aperture of the lens, then there are possibilities that the marginal rays are also coming into the view. So marginal rays are those rays which are very or at the edge of the ray, edge of the lens. So the rays which are very far away from the principal axis, like this. Okay, these rays are actually called marginal rays, and the rays which are near to the principal axis, so these are called paraxial rays. So these are marginal rays. Marginal rays. So these marginal rays, when they are refracted through the lens, they actually are focused at different points than the real focus of this lens. Suppose these were actually focused somewhere here. I'm sorry. I'm showing you here. Suppose this ray is A, this is B, and this is C. These are three sets of. So here also A, B, and C. Look, this A going where? It is actually getting focused over here. Okay, see this ray. Okay, so this is point somewhere here. See, for the other rays B and C's. Okay, C, look, they are actually focusing here. Okay, and B are focusing here. So when all the rays are not focused at the same point or at the same focus, then what is happening? The image will be blurred image. Okay, image becomes blurred. Okay, not very clear image you will be able to see. You will not be able to see a clear image. So this is called spherical aberration. This is purely due to the large aperture, because these rays are not cut off here. So the marginal rays are also coming, which are focused on the principal axis, but at the different position compared to that of the paraxial rays, and therefore you will see blurred image. So this is called spherical aberration. So the second demerit is that there could be chromatic aberration. What is chromatic aberration? See, through lens there will be refraction, right? And you know, not only refraction, there could be a chance of dispersion as well. Dispersion. Okay, so what is dispersion? Dispersion means, suppose there is, say, white light, but after refraction it will actually break into its component lights. Okay, like all this violet to red, all the lights you will be able to see, and because of that also you will not be able to see a very clear image. Okay, you will see very fuzzy image. Okay, because if all the colors are mixed, then you cannot distinguish various points. Okay, or you cannot see clearly. So this is actually due to refraction or dispersion. So actually refraction and dispersion, they are related phenomenon. So in case of lens, these two are very prominent demerits. Okay, not only that, there are few more demerits cost wise, because if you want to make a perfect lens, and that too of a very big size, because objective needs a bigger aperture, right, to collect lot of light, okay, as much as possible to make the image very bright. So making a perfect lens of large aperture is really costly and also difficult. Not only costly, that is difficult also. So making large. Okay, objective is large in size. Objective lens is large in size. Hence, you know, the telescope itself will be of very large size and also heavy. When your lens is very large, it will be very heavy, and you have to actually hold it, right, mechanically. So to hold the lens mechanically, it is becoming difficult as well. Okay, so because of this, because of this, the refracting telescopes are having difficulties. So difficulties in handling also. If it is so big, so large and so delicate, you cannot handle it, or you cannot just move from one place to another. Okay, because of this demerits, we need to see the alternates. So alternates was reflecting telescopes. So what was done in reflecting telescope? Look, I'll just tell you the remedy also, what we have made in reflecting telescope. So in place of lens in reflecting telescope, see, for the first one and second one, for both, so both the aberrations or both kind of demerits, both the demerits were removed by only one arrangement or one solution, that is using, so replacing objective lens by concave by a concave paraboloid mirror. See, instead of using large aperture or large size objective lens, we have to use concave paraboloid mirror. Not only mirror, look here. See, even if we have a large aperture spherical mirror, see, this is large aperture spherical mirror, this is of small aperture spherical mirror. In case of small aperture spherical mirror, we have paraxial rays, okay, which are focused at the focus of this mirror, spherical mirror, exactly at the focal point, right? Because these are of small aperture. When you use bigger aperture of spherical mirror or large aperture of spherical mirror, look what happens in this case also. This marginal rays will come in picture, and see, there will be, see, this length, okay, this, there is a spread of this focal length, okay, because of, see, some rays are focusing here, some rays are focusing here, some rays are focusing here. In case of spherical mirror also, if you take a bigger size or larger aperture, then there could be spherical mirror. So instead of using even spherical mirror, concave spherical mirror, we have taken paraboloid mirror. You look, parabolic mirror, in case of parabolic mirror, all the rays will be whatever rays. See, this ray is maybe paraxial, this one is paraxial, this one is paraxial, they are focused here. And also you look, this one, this is the marginal ray, so this marginal ray also is focused at the same point. So instead of using, see, we are using mirror to avoid or to cut off the spherical aberration, to remove the spherical aberration, but we are not using concave spherical mirror alone. We are using, actually we are using parabolic mirror, okay, we are using parabolic, this is the main mirror, we are using parabolic mirror, paraboloid, that's why it is called concave paraboloid mirror, okay. So we are replacing, in the reflecting type of telescope, we are replacing the the objective lens by a concave paraboloid mirror. See, with this, as I have explained now, the spherical aberration is removed, but how come this chromatic aberration is going to be removed from here? Because, see, in the mirror there is no refraction at all, right? So there is no chance of, for a good mirror, at least for a very good quality mirror, there is no chance of refraction. And then see, if there is no refraction, then this chromatic aberration is not going to come into the picture. So when we talk about costly to make a large aperture lens, see, in case of mirror, to make a large aperture mirror and having good quality is much lesser costly than making the lens of good quality in that particular aperture, isn't it? And see, since it is very large size, see, in case of lens is to become very heavy, very heavy. To mount it mechanically, it was difficult. But in case of mirror, having large aperture is actually comparatively less heavy, okay, or what is comparatively less than the lenses. So therefore it is easier to hold mechanically, okay, mount mechanically, and it is easier to handle also, because what is little less, actually much less than the lenses. So these were actually the necessities to, or these are, I can say, these are the demerits what we have encountered in case of refracting telescopes. So we had to go for reflecting telescope to remove these demerits, okay, or limitations. All right, now we'll see. So as I mentioned, Newton was the first person to make reflecting type telescopes, and you know, as I said, that instead of objective lens, we have objective concave mirror. See, this is paraboloid concave mirror, boloid concave mirror, okay. You can see this schematic diagram here. See, this is the mirror, and when so it has actually large aperture, and when the beam of light are reflected, you know, when they are coming here and reflecting from this particular points, they, since it is converging mirror, concave mirror, so the ray will be going to meet at the focus, because I have taken the parallel rays from the distant object. So before they meet, just before the focal point or the focus of this objective mirror, a plane mirror was kept at 45-degree angle to the principal axis, okay, 45-degree angle, such that they will come and reflect. So this is actually plane mirror, okay. A plane mirror was kept just before the focal point. See, this is the focal point. Before the focal point, these rays were actually reflected by this plane mirror, and an eyepiece, this is lens, okay, of small aperture, an eyepiece was placed, and the eyepiece was placed at exactly 90-degree to this principal axis, okay, 90-degree to this principal axis, so that, and the eyepiece was so placed that the reflected rays from the plane mirror will come and enter over here, and the final image will be seen by the observer, okay, through this eyepiece, okay. So the final image will be, in this case, how will be the final image? The final image will be virtual, erect, and highly magnified. Virtual, erect, and highly magnified. Highly magnified image. Okay, this is about Newtonian telescope. So what was the modification made in compared to refracting telescope? This is the modification. Okay. Okay, the concave mirror. Not only concave mirror, even this plane mirror is being used to just take away the rays before they meet over here and create an image. This is a virtual image, and this virtual image will actually act as virtual object for this mirror. That's what we can see. Okay. All right. So this reflected ray with reflected rays from the plane mirror will pass through the eyepiece, and here the observer will sit and observe the or see the distant object. Okay. Now we will just go to the next category, that is Cassegrain telescope. So in this case, it consists of a large concave paraboloid mirror, primary mirror. This is called primary mirror. Okay, this is the mirror. Okay, primary mirror. Sorry. This is primary mirror. Okay, and this is acting as objective here. So objective mirror. In place of objective lens, we have kept this, and with the center at the center. Okay, here one hole is made. This is the hole. I'll tell you why this hole is required. Look, this is the primary objective mirror, which is being used in place of objective lens. Okay, so in this case, look, the parallel rays are coming. Okay, they are reflected by this mirror. This is the mirror actually. Okay, so as they are reflected, so after reflection, what will they do? See, this is the schematic one, another one. So just to show the complete figure, see, after reflection, they are, so this is the primary focus of the primary focus. Okay, or prime focus. Okay, sorry, this is prime focus, or the focus for the focus of the primary objective mirror. So naturally, the parallel rays after reflection, they will come and meet over here and try to make an image over here. But anyway, here also, just like this plane mirror, here instead of using plane mirror, one convex mirror, which is called secondary mirror also, this convex mirror is being kept just before the focus. So after reflection, since these are actually rays, okay, so after reflection, what this ray will do, they will go through this hole. Actually, they will go this direction. Okay, after reflection from the secondary mirror. So that's why we require a hole at the middle of this primary objective lens. In case of Newtonian mirror, this was plane mirror. Okay, here, so that plane mirror was kept at 45-degree angle, but this is actually a convex mirror. It is actually convex mirror. Convex mirror. Okay, this convex mirror will reflect the rays which are coming to meet here at the prime focus to make an image. So these rays will be reflected back this direction, and here you look, there is an eyepiece over here. So this is, see here, there will be a lens eyepiece. Okay, so through eyepiece also will actually magnify the final image. Okay, so here will be an eyepiece over here. So what is happening in this case? So the parallel rays from distant object are reflected by the large concave mirror, and because these rays are coming to meet at the prime focus, they are reflected by the small convex mirror and converged at a point. I suppose here the image I has been formed, final image. Okay, so this image, let us say this is I prime and this is I. This I prime is virtual image because this is not the actual image here, and this virtual image will act as object for this mirror, virtual object for this mirror. Okay, so the final image formed here is viewed through the eyepiece, as the first image at F is inverted. See, at this place the image, this I prime will be actually inverted, and hence final image in this case will be also inverted with respect to the object. Okay, so because this image is inverted image, so this also final image also will be inverted. So what will be the final image here? Final image. So final image will be inverted with respect to the object. So this is only difference we can see in case of Newtonian and like in between Newtonian and Cassegrain telescope, that in this case inverted image will be produced. Inverted image. In case of Newtonian telescope, we have seen the image will be virtually erect and highly magnified. Here also the image will be highly magnified, but real and inverted image will be produced here. Okay, so this is the construction and working principle or working of the reflecting telescope. Now we'll see the magnification of the final image found by Cassegrain telescope. So magnifying power, see, if you remember, we have focal length FO. This is actually focal length of objective. We'll use the same notation here also. This is the focal length of eyepiece, objective, eyepiece. Okay, so in terms of that, see, there are two settings, you know, we have already discussed when we had discussed astronomical telescopes and microscopes also. There are two settings. One is magnifying power maximum, or when this will be maximum magnifying power when the final image formed at the least distance of distinct vision. So magnifying power for the image formed least distance of distinct vision. So formula is the same actually. There is no difference in that. So FO by FE whole into 1 plus F E by D. D is the least distance of distant vision, that is 25 centimeter for normal eye. Okay, so the second point is the magnification when final image for the final image for the final image formed at infinity. What is the magnification here? FO by FE. Okay, or FO means R by 2. This is the radius of curvature of the objective mirror divided by FE, the focal length of the eyepiece. So due to large aperture of mirror, they can actually, mirror has very better capacity or efficiency to collect light, okay, and make the image very bright. So I'll tell you few advantages here. Advantages. First point is large mirror. Large mirror means large aperture mirror has better light gathering power. Sorry, gathering power and less absorption, okay, less absorption of light compared to lens, compared to lens. So because of that, what happens? The final image formed by reflecting telescope is very bright, very bright. Okay. Second point is that due to large aperture, there is a high resolving power. Resolving power. Resolving power means, in short, I'll tell you, if there are two stars, suppose there are two stars very close to each other, and when you see from very far, you might think that these are two together. You'll see like this. You'll see a diffused image out of these 2 point image. Okay, point object. Suppose these are 2 point object, but you'll see them together, some diffused object. Okay, you'll see some diffuse object. Instead of seeing a point, you'll see some fuzzy things like this. Okay, and together you will see. So if the resolving power is less, if the resolving power is better, then you can actually view very closely spaced 2 point object clearly like this. You can see them as different object. Okay, from the okay, you can see them different. Okay, otherwise you will see together, and like spreaded image kind of that. So in case of mirror, you require grinding. Okay, in case of mirror, you require grinding and polishing of one surface. Actually, so making lens is very tough, whereas you can just take some spherical things or parabolic thing and you just make polish of one surface. That is enough to give you better quality mirror. Okay. Okay, so and these are actually advantages that even if it is large aperture, so it has actually less weight. So because of this less weight, easy to handle, first of all, easy to mount, less risky about breaking and all. Okay, and second thing is easy handling. So this were already discussed. Okay, so this is how we cover this chapter, ray optics. So I think we'll just stop it here for today. Next day we'll start with a new chapter. So that may be electromagnetic wave or something we'll take in the next class. In the electromagnetic wave, I think we have discussed already. We'll take up wave optics itself. So in the next class we will start with wave optics. We'll start with wave optics. So there we can actually, okay, we'll just discuss it in the next class itself. So thank you for your patience. Bye for today.